Okay, so for those who have come late, so we'll be looking at the learning objectives will be for today's class is understanding the concepts of polarization, refractive index, and birefringence. And we also look at some of the electro-optic effects, which is Kerr effect, Pockels effect, and Faraday effect. Okay. So first we look at polarization. So to look at polarization, I will try to show you a video because it needs some amount of visualization. Okay, so just give me a second.
Talk about polarization of light. We know what light waves are. They're electromagnetic waves, so they're made out of electric fields. And that's not good enough. We know they're not just electric fields that couldn't sustain itself. There's got to be magnetic fields there as well that are changing, and those are perpendicular, so you can kind of draw them. It's hard on something two-dimensional, but you can kind of imagine those looking something like this, and those magnetic fields would point at a right angle to the electric fields. But this gets really messy if I try to draw both the electric and magnetic fields at the same time, and so we're going to leave the magnetic fields out. It's often good enough to just know the direction of the electric field, and we focus on the electric field. So what does polarization mean? Polarization refers to the fact that if this light ray was heading straight toward your eye, or a detector over here, what would you see? Well, if I draw an axis over here, and this point here in the middle, this is this line. So imagine we're looking straight down that line, and then up and down is up and down, and then left and right, that direction I had the magnetic field would be this way and that way. What would my eye see? Well, my eye's only going to see electric fields that either point up or electric fields that point down. They might have different values, but I'm only going to see electric fields that point up or down. Because of that, this light ray is polarized. So polarized light is light where the electric field is only oscillating in one direction, up or down. That's one direction, vertically. Or it could be polarized horizontally, or it could be polarized diagonally, but either way, you could have this wave polarized along any direction. I mean, a light ray like this, if we had it coming in diagonal, this light ray that's oscillating like this, where the electric field oscillates like that, that's also polarized. These are both polarized because there's only one direction that the electric field is oscillating in. And you might think, well, how could you ever have a light ray that's not polarized? Easy. Most light that you get is not polarized. That is to say, light that's coming from the sun, straight from the sun, typically not polarized. Light from a light bulb, an old incandescent light bulb. This thing's hot. You can get light polarized in every direction all at once, all overlapping. So if we draw this case for a light bulb, just a random incandescent light bulb, you might get light. Some of the light hitting your eye, you can get some light that's got that direction. You got light that's got this direction. You got light in all these directions at any given moment. I mean, you'd have to add these up to get the total, and they might not all be the same value. But what I'm trying to say is at any given moment, you don't know what direction the electric field is going to be hitting your eye at from a random source. It could be in any direction. So this is not polarized. This diagram represents light that is not polarized. At some point, the field might be pointing this way. At some later point, it's this way. It's just random. You never know which way the electric field is going to be pointing. Whereas these over here, these are polarized. So how could you polarize this light? Let's say you wanted light that was polarized. You were doing an experiment, you needed polarized light. Well, that's easy. You can use what's called a polarizer. And this is a material that lets light through, but it only lets light through in one orientation. So you can have a polarizer that, for instance, only lets through vertically polarized light. So this is a polarizer. These are cheap. Then plastic configured in a way so that it only lets light through that's vertically polarized. Any light coming in here that's not vertically polarized gets blocked or absorbed. So what this means is if you use this polarizer and held it in between your eye and this light bulb, you would only get this light. All the rest of it would get blocked. Or you can just rotate this thing and imagine a polarizer that only lets through horizontal light. Now it would only let through light that was this way, and so you would only get this part of the light. Or you could just orient it at any angle you want and block everything but the certain angle that this polarizer is defined as letting light through. So you can do this, and once you hold this up, you get polarized light. Light that's only got one orientation. So that's what polarization means. But why do we care about polarization? Well, let me get rid of this for a minute. You've heard of polarized sunglasses, so imagine you're standing near water, or maybe you're standing on ice or snow or something reflective. There's a problem. Say the sun's out, it's shining, it's a beautiful day, except there's going to be glare. Let's say you're looking down at something here on the ground. Well, it's going to get light reflecting off of it from just, light's coming in from all directions, but it also gets this direct light from the sun. So it gets light from reflected off the clouds and whatever's nearby, ambient light. And then there's also this direct sunlight. That's harsh. If that reflects straight up to your eye, that hurts. We don't like that. It blocks our vision. It's hard to see. It's glare. We don't want this glare. So what can we do? Well, it just so happens that when light reflects off of a surface, even though the light from the sun is not polarized, once it reflects, it does get polarized, or at least partially polarized. So this surface here, once this light reflects, it's coming in at all orientations. You got electric field. You never know what electric field you're going to get straight from the sun. And when it reflects, though, you mostly get, upon reflection, the direction of polarization defined by the plane of the surface that it hit. So because the floor is, horizontal, when this light ray hits the ground and reflects, that reflected light gets partially polarized. This horizontal component of the electric field is going to be more present than the other components. Maybe not completely. Sometimes it could be completely polarized, but often it's just partially polarized. But that's pretty cool, because now you know what we can do. I know how to block this. We just get some sunglasses. We put some sunglasses on, and we make our glasses so that these are polarized. And how do we want these polarized? I want to get rid of the glare. So what I do is I make sure my sunglasses only let through vertically polarized light. Here's some polarizers. That way, a lot of this glare gets blocked because it does not have a vertical orientation. It has a horizontal orientation, and then we can block it. So that's one good thing that polarization does for us in understanding it. We can get rid of glare. Also, fishermen like it, because if you're trying to look in the water at fish, you want to see in through the water. You want to see this light from the fish getting to you. You don't want to see the glare off of the sun getting to you. So polarized sunglasses are useful. Also, we can play a trick on our eye if we really wanted to. You could take one of these, make one eye have a vertical orientation for the polarization, have the other eye with a horizontal, and you're thinking, this is stupid. What would you do this for? This eye's going to get a lot of glare. Well, you wouldn't use these outside when you're like skiing or fishing, but you could play a trick on your eyes if you went to the movies and you went and watched a movie. Well, the reason our eyes see 3D is because they're spaced a little bit apart. They each get a slightly different image. That makes us see in 3D. Well, we can play the same trick on our eye if we have the polarization like this. If some of the light from the movie theater screens coming in with one polarization and the other light's coming in with the other polarization, we can send two different images to our eyes at the same time. If you took these off, it'd look like garbage because you'd be getting both of these slightly different images. It'd look all blurry, and it does. If you take off your 3D glasses and look at a 3D movie, it looks terrible, because now both eyes are getting both images. But if you put your glasses back on, now this eye only gets the orientation that it's supposed to get, and this eye only gets the orientation that it's supposed to get, and you get a 3D image. So it's useful in many ways. And let me show you one more thing here. Let's come back to here. This light was polarized vertically, and so that's called linear polarization. Anytime, same with these. These are all linear polarization because just up and down. One linear direction, just diagonal. This is also linear. All of these are linear. You can get circular polarized light. So if we come back to here, we've got our electric field pointing up like that. Now let's say we sent in another light ray that also had a polarization, but not in this direction. Let's say our other light ray had polarization in this direction. So it looks like this. Kind of like what our magnetic field would have looked like, but this is a completely different light ray with its own polarization and its own magnetic field. So say we sent this in, what would happen? Well, at this point, you'd have electric field that points this way. At this point, you'd have electric field that points that way. What would your eye see if you were over here? Let's see, if I draw our axis here. All right, when this point right here gets to your eye, what am I going to see? Well, I'm going to have a light ray that's one part of the light ray, one component points up, that's this electric field. One component points left, that's this electric field. So the total, my total electric field would point this way. I could do the Pythagorean theorem if I wanted to figure out the size of it, but I just want to know the direction for now. And then it gets to here, and look at, they both have 0. This light ray has 0 electric field, this one has 0 electric field, so then it just be at 0. Now what happens over here? Well, I've got light. This one points to the right at that point. This pink one. And then this red one would be pointing down. So what would I have at that point? I'd have light that went this way. And it would just be doing this over and over. It would just be, I just have diagonally polarized light. This isn't giving me anything new. You might think this is dumb. Why do this? Why send in 2 different waves to just get diagonally polarized light? I could have just sent in one wave that was diagonally polarized and got the same thing. The reason is, if you shift this purple wave, this pink wave, by 90 degrees of phase, by pi over 2 in phase, something magical happens. Let me show you what happens here. If we move this to here, now we don't just get diagonally linear polarized light. What we're going to get is, let me get rid of this. Okay, so we start off with red, right? The red electric field points up, and then this pink wave's electric field is 0 at that point. So this is all I have. My total electric field would just be up. I'm going to draw it right here. The green will be the total. Now I come over to here, and at this point, there's some red electric field that points up, but there's some of this other electric field that points this way, so I'd have a total electric field that would point that way. And then I get over to here, and I'd have all of the electric field from the pink one, none from the red one. It would point all left then. Look what's happening. The polarization of this light, if I shift this, if I'm sitting here looking with my eye, as my eye receives this light, I'm going to see this light rotate its polarization. The polarization, I'm going to notice, swings around in this circular pattern, and because of this, we call this circular polarization. So this is another type of polarization where the actual angle of polarization rotates smoothly as this light ray enters your eye. And you know what? Alright, actually, I said you'd receive this one first. That makes no sense. You're going to receive the ones closest to you first in this light ray going this way. So you'd actually receive this one first, then that one, then this one, then this one. Because of that, you wouldn't see this going in a counterclockwise way. You'd see this going in a clockwise, circularly polarized way. Sorry about that. And you might think, okay, why? Why even bother with circular polarization? Well, I kind of lied earlier. It turns out in the movie theater example, they don't actually do it like this typically. Oftentimes in the movie theaters, we don't have just linearly polarized sunglasses. This would be a problem because when you look at the movie theater screen, and if you were to tilt your head just a little bit, think about it, this one's not really going to get the right image anymore. It's going to get some of both, and this one's going to get some of both. It's going to be blurry. Your head would have to be at perfectly level the whole time, which might be annoying. So what we do is instead, we create circular polarized glasses so that this one would only get one polarization, this one would get the other direction. This way, even if you tilt your head a little bit, shoot, clockwise is clockwise, counterclockwise is counterclockwise. By using circular polarization for 3D movies, it can make it a little easier on your eyes to see a better 3D image, even if your head's tilted a little bit.
Okay, so I hope you have understood what it was mentioned in the video. Okay, I know the audio was a bit bad, but I hope you have got the concept that any light can have a kind of polarization where it is actually the orientation of the electric field. Okay, so you can have linear and circular. Also, there is something called as elliptical polarization, where in elliptical polarization, you see that in circular polarization, if you shift the second ray by 90 degree, you'll get a circular polarization. If you shift the second ray by any other angle, you'll get an elliptical polarization. Okay, this is just a basic concept of polarization. Just I want to discuss so that it will be easy for you if you go further. Okay, next concept is regarding refractive index. This you might have studied all through your 10th to your second year, third year BTech. But just to reiterate what a refractive index is. So the ratio of the speed of light in vacuum to its speed in specific medium is called as a refractive index. So it is actually the property of the material. So it's a material property. So if you say that the speed of light in a material is half to that of the speed of light, actual speed of light, then you say the refractive index is 2. Okay. In electromagnetic waves, the speed is dependent on the optical density of the medium. So what is an optical density? Optical density is the tendency of the atoms in a material to restore the absorbed electromagnetic energy. Okay. So when the light passes through any material, there can be a change in speed, mainly because the light will be absorbed by the material. And some part of the light which is absorbed, or the atoms in that material has a tendency to restore the absorbed light. And that is called as an optical density. So how many amount of atoms are able to restore the absorbed electromagnetic energy. So the more optically dense material is the slower speed of light, because when you have a large amount of optically dense material, then you have a large amount of atoms which will try to absorb and then try to emit, etc., which will hinder the speed of the light. So one such indicator of the optical density of a medium is the refractive index, because it is directly related to the speed of the light. The refractive index determines how much the path of light is bent or refracted when entering the material. So when a light travels to the material, it might be possible that because of the refractive index or the optical density of the medium, there will be absorption of the light, and the path of the light will be bent once it enters and leaves the medium. Okay, so that's a measure. And the most famous law concerning the refractive index is the Snell's law, which says that when a light is incident on an interface with two different refractive index N1 and N2, some part of the light will be transmitted. Sorry, some part of the light will be reflected, and some part of the light will be transmitted. And the reflected angle and the transmitted angle is the incident angle, and the reflected angle is the same, and you will have some amount of transmitted light with some angle with the normal. This is basically the Snell's law. So the next concept is regarding isotropic and anisotropic materials. We need to know what is the difference between these two. Okay, so isotropic are all the materials whose the properties in all the directions are same. For example, if you look at the refractive index of an isotropic material, if you look at any position or at any given direction, the refractive index of an isotropic material is same. But for an isotropic material, the different properties are different in different directions. Particularly, in isotropic, you have single refractive index, but in anisotropic, you have many refractive indices. So if you look at one direction, you have one refractive index, and if you look at a different direction, you will have a different refractive index. Okay, so same refractive index means you have the same velocity of light. Different refractive index means you have a different velocity of light in different direction. So what is the consequence of having different refractive index? Or if you have a same single refractive index, it does not split the unpolarized light. Okay, so we have seen in that video that you can have multiple or you can have mixed polarization. There is no polarization for the light, and you can always create a polarized light from an unpolarized light. You can create a linear polarized light or a circular polarized light or an elliptical polarized light from an unpolarized light. If it is an isotropic material, if an unpolarized light falls on isotropic material, it will not change its polarization. It means it will still be unpolarized light. But if it is an anisotropic material, it will split the unpolarized light. So you can make the unpolarized light to be of linear, circular, or a different unpolarized light, and you can split its polarization. So you can have a linear polarized light and unpolarized light, or a circular polarized light and unpolarized light, or a circular polarized light and a linear polarized light. So you can have all those combinations. And it doesn't show any, the isotropic material doesn't show much of any characteristic for birefringence, optical activity, dichroism, and dispersion. We'll see what birefringence is. But in an anisotropic material, it will show the properties of birefringence, optical activity, dichroism, and dispersion. Okay. So what is birefringence? So it is basically the term called as double refraction. Okay. So refraction is actually the bending of the light, and double refraction means you are actually bending it twice, or you are making the light bend such that you will have two different rays. So some materials have the optical property such that the refractive index depends on the polarization and propagation direction of the light. So there are some materials in which the refractive index is still depend on the light incident, basically the polarization of the light and the propagation direction of the light. And these optically anisotropic materials are said to be birefringent. So the important thing is all these materials are anisotropic. So they will have different refractive indices in different directions. So depending on the polarization of the light which it is being passed, the refractive index will change, and it will cause something called as birefringence. The birefringence is often quantified as the maximum difference between the refractive indices exhibited by the material. When the light falls on the material, depending on the polarization of the light, there can be change in refractive indices. If you take the lower refractive index and the higher refractive index, that is possible because of passing that light, that is basically the difference. The maximum difference is called as the birefringence. Birefringence is responsible for the phenomenon of double refraction, whereby a ray of light when incident upon a birefringent material is split by polarization into two rays taking slightly different paths. So when a single ray of light is incident on a birefringent material, it is split by its polarization to two different rays, and they will propagate in two different paths. Okay, so if you see this example, this is taken from Wiki. So you see that there is one light which is basically incident, and at the outside you are getting two different light. So this material is actually a birefringent material. Okay, or you can see that it actually inside it splits into multiple rays, and actually coming out is also multiple, but you can see only two. So such kind of material or such kind of property is called as birefringence, and a material is called as a birefringent material. Okay, so this is the some of the basic stuff for our today's discussion. Now we come to something called as electro-optic effect. So what is an electro-optic effect? It means induced change in the refractive index of a material with applied electric or magnetic field. So when you apply an electric field or magnetic field, the refractive index of the material will change. And not all the materials have that property. Only some materials have that property. Mostly the materials are anisotropic materials. And when you apply the field, magnetic or electric, the refractive index of material will change. The change in the refractive index dependent on the polarization of the incident light is called as birefringence. This we have already seen. So the refractive index can change by polarization of the incident light. Refractive index can change by applying an electromagnetic field. So there are some materials in which the refractive index varies according to the application of electric field or because of the incident light. There are three different kinds of effects. First one is Kerr effect, second is Pockels effect, and third is Faraday effect. So we will see one by one. So the first one is called as the Kerr effect. So when a material is under the action of an electric field, an optic axis may be induced parallel to the direction of the field. This effect is known as the Kerr effect. We'll see what an optic axis is. Okay, so it means that when you apply an electric field on some materials, parallel to that field, there will be an optic axis which is induced. Optic axis is the axis through which the light will propagate. That is called as optic axis. Okay, the Kerr effect is also called as quadratic electro-optic effect, QEO effect. Is a change in the refractive index of a material in response to an applied electric field. So the change in optic axis means there's a change in refractive index. So when you apply an electric field, there is a change in refractive index, which in turn changes the optic axis. This is called as a Kerr effect. An optic axis may be defined as the direction in a crystal in which, when light is propagated in the same direction, the refractive index is independent of the direction of the polarization of the light. Okay, the optic axis is an axis, may be defined as an axis in the crystal in which, when light is propagated in the direction of the optic axis, the refractive index, which usually depends on the polarization of the light, is now independent of the polarization of the light. Okay, so usually most of the anisotropic material are birefringent, means the refractive index will depend on the polarization of the light. But if the light is propagating through the optic axis, then it will not depend on the polarization of the light. The refractive index will not depend on the polarization of the light. Okay. So if to demonstrate the Kerr effect, consider this cubical material. Okay. And the line drawn across the face of the crystal indicate the direction of optic axis. So basically, the optic axis is this. So these are the different optic axes. Okay, the slanting lines. The plane polarized light on entering the crystal can be resolved into two components. So this is the direction of propagation. So if you look at from here, so if you are looking from here, okay, then you see that you can see such a structure like this. Okay, and you see that the direction of propagation is this. So that and the plane of polarization is this. So this is this one. Okay. So it can be resolved into two perpendicular components. One is along the direction of the light, and one is along the either direction of the perpendicular direction. Okay. So one component is parallel to the optic axis and is termed as ordinary component. So this is the optic axis, and this component is parallel to the optic axis. Okay. So this is the optic axis, and this component is parallel to the optic axis. This is called as ordinary component. And the other is perpendicular to the optic axis and is termed as the extraordinary component or extraordinary ray. This is perpendicular to the optic axis. So basically your optic axis is like this. There's a component like this. This is perpendicular to the optic axis. This is called as extraordinary component. Okay. So this is the direction of optic axis. When you view it from here, you will see a elliptically polarized light. Okay, so this is basically a direction of the light, and the material will cause changes in the polarization of the light. Now, the velocity of propagation of the two components within the crystal are different. Okay, because the one which is propagating through the optical axis, which is this component, let me use the same color, which is this component, will not have a different refractive index. So as long as it is propagating along the optical axis, it will have the same refractive index, which means it will have the same velocity. But the component which is perpendicular to the optic axis will encounter different refractive indices at different points, which means the velocity of the light will change. So the velocity of propagation of both the components will be different. On emerging from the crystal, the ordinary and extraordinary components are, in general, out of phase. Hence, the output light is elliptically polarized. So once this component emerges out of this material, the first component, which is the parallel component, will not have a different velocity, but the perpendicular component will be of different velocity, means there will be out of phase. Okay, so if it is something like this, the electric field, the parallel component will have some phase like this, and the perpendicular component will be of some other phase. For example, something, or let me, something like this. Okay, and they will have a different component altogether. So when you see this, somebody viewing from here will see an elliptically polarized light. Okay, so that's how we can. So that is this is not the Kerr effect. This is how the material behaves even if it is not supplied with an electric field. Now, in the Kerr effect, the applied electric field produces an optic axis or an additional optic axis. Okay, so if you see this material, you see that in the previous diagram, the optic axis was slanted. Now it is parallel to the sides. Okay, the amount of phase retardation between the ordinary and extraordinary component is, among other things, proportional to the square of the applied voltage. Okay, so again, you can resolve any polarization into components along the optic axis and components perpendicular to the optic axis. Okay, when the light passes through with this polarization, again the same thing will happen, where the one which is parallel parallel to the optic axis will emerge without any change in velocity, but one which is perpendicular or with another direction of the optic axis will emerge with a different velocity. Finally, you will end up having a phase difference between both the components. But in the last diagram, we don't know what the phase difference is. That is the property of the material. But in this diagram, we know what is the phase difference. The Kerr effect makes sure that whatever phase difference, the delta phi, is there between the components when it emerges out is proportional to the square of applied voltage. Okay, so there is a voltage applied at the ends, and depending on the square, depending on the voltage applied or the square of the voltage applied, the phase difference will change. Okay, so if we say that delta phi is equal to, let's say, 30 degree at voltage is equal to 2 volt, then the delta phi will be like 60 degree at voltage equal to 4 volt, means proportional. So if voltage increases, V is equal to 2 volt, it is proportional to V square. So the new delta phi, we write it again. So let's say delta phi is equal to 30 degree at V square is equal to 2 volt. Then delta phi will be equal to 60 degree at V square is equal to 4 volt. Okay. So this is the proportional change. And the good thing about this thing is we know what is the phase difference. We can express the phase difference in terms of the constant K, the propagation constant K, the length of the crystal through which the light is propagates, which is L, the applied voltage, which is V, the wavelength of the light, which is lambda, and D is the width of the crystal. So you will know the phase difference between the two components of the polarization once it emerges out of the material. This is called as the Kerr effect. So here the important thing to note here is the delta phi is proportional to the square of voltage applied. This is called as Kerr effect. Now Pockels effect is exactly same of Kerr effect, except that the phase shift depends directly on the voltage. Means whatever delta phi is there, it is proportional to voltage. It's not proportional to square of voltage, and it's called as linear electro-optic effect. Okay, there are two modes for Pockels effect. First is called as transverse Pockels effect. So in this case, if the electrode configuration is such that the applied field is normal to the direction of propagation of incident light, this is called as transverse Pockels effect, which basically it is same as Kerr effect. Second case, the electrode configuration is such that the applied electric field is parallel to the direction of propagation of incident light. Okay, so applied the electrode means like wherever you are giving the voltage, plus voltage and minus voltage. So if you place the electrode such that the applied field is normal to the direction of propagation, which we have seen till now, which is means you have electrode here, here, and here, and this is the direction of propagation. So the electrodes are aligned like this, and the direction of propagation is aligned like this, which is means it is perpendicular. It is called as transverse Pockels effect. But if you align the electrode in such a way that both are in parallel, the direction of propagation and electrode applied electric field is parallel, it is called as longitudinal Pockels effect. So you can see this diagram here. So you see that in this case, this is transverse Pockels effect. You have the direction of propagation here, and you have the applied electric field here. So basically, both are perpendicular. And longitudinal Pockels effect, you have the electric field and the direction of propagation in the same direction. This is longitudinal Pockels effect. So in both the cases, you have a shift in phase between the two modes, between the two components, and both are proportional to V. Okay, the only difference is that this is pi n0 cube, which is a refractive index, L is the length along which the light is being propagated. D is the width of the material. Lambda is the wavelength of the light transmitted. And for longitudinal case, you will have an extra 2 multiply. That's all. Okay, this is called as Pockels effect. The last one is the Faraday effect. It says instead of an electric field here, we are going to use a magnetic field. When a magnetic field is applied to many solid gases and liquids, the plane of polarization of an incident beam of light is rotated. Okay, so if you have some structure like this, okay, and the light is incident and goes out like this. Okay, now the polarization direction is this. Now you apply a magnetic field on this. So what happens is the plane of polarization will rotate. So it can rotate something like this or this or this. So in any direction it can rotate. So if it rotates, it is called as Faraday effect. And if the angle of rotation is denoted by theta, the magnetic field in the direction of light path by B, then theta is equal to V into L into B, where B is called as a separate constant called as the Red's constant. L is the path length within the material. So let's say the rotation angle is, let's say, theta, okay, or I would say the rotation angle should be measured from the normal. So if this is theta, then theta is given by the applied magnetic field along the direction of propagation, the length, which is basically the path length, which is L here, and the Verdet's constant. So you can calculate how much angle it will rotate. So all these effects have an advantage that we will know the phase shift or the angle of rotation in all the cases, which is important because we will know the polarization. Okay, so these are different effects in uh, of electro-optic effect, and so please go through this and let me know if you have any doubts. Okay, so we'll stop it here today, and let me take the attendance. Okay,